So friends, let's look at the correction of the Southwest mock, the Cameroon Advanced Level GCE Southwest mock chemistry. So let's look at the paper 2, guys. Let's look at the physical chemistry of this particular paper 2024 this year. Okay. Now guys, the first question simply reads that we should define the following terms. You have the mole of a substance, then in Roman 2 you have molar mass. Okay guys, let's start. So for the mole of a substance is defined as the amount of substance which contains as many elementary particles as there are atoms of carbon in exactly 12 grams of the carbon 12 isotope. Great. So guys, this is a definition that is known since from our junior secondary school. This definition is known. Great. Then the next one talks about the molar mass. So guys, the molar mass simply refers to the mass of 1 mole of any given substance. For instance, if you take 1 mole of calcium, the molar mass is 40 grams per mole. If you take a substance like, let's say, sodium chloride, the molar mass of sodium chloride is given as the sum of the individual masses of the various atoms that make up sodium chloride compound. Great. So guys, that's it. The next part reads that in an experiment to determine the molar mass of a volatile liquid X, 0.46 grams of the liquid was injected into a graduated glass syringe. On evaporation, it occupies a volume of 204 centimeters cube at 20 degrees Celsius and 760 millimeters mercury. Roman 1. How would you know if the liquid has completely vaporized? Okay, guys, we are going to know when the liquid has completely uh, vaporized uh, if the volume of the gas syringe, guys, does not change. Okay, that's when we are going to know that all the liquid has completely vaporized, because during the process of vaporization, guys, we expect that the gas syringe, that's the piston on the gas syringe, guys, has to be moving constantly, which is simply indicating that more liquids have been vaporized. So at that point where for all the liquids have been vaporized, guys, the piston on the gas syringe, guys, is held constant. It does not change again. Shows that no liquid is being vaporized again. Great. So guys, then the next part, the Roman twist, now should calculate the molar mass of X. Okay. So guys, since this question talks about a liquid that is being vaporized, so we are going to use the formula PV equal to nRT, where P is the pressure, V is the volume, N the number of moles, R is the molar gas constant, and the T, guys, is the temperature in Kelvin. So in this case, guys, we can know that our moles, which is small n, is given as what? Given mass per molar mass, right? If you call the given mass small m and molar mass capital M, and we make our capital M the subject, we're going to have capital M to be equal to small m RT over PV. Now, guys, there's some conversions that we must have to take into account. Knowing that our M in this case has to be in grams, our R has to be what, guys? Has to be the version that talks about 0.084. Okay, 0.084. Great. So that's the version in which we need. We don't need the one that has the 8 point something. Okay, that's not the version in which we need. The one we need has to be 0.0840. What we're going to use here has to be 0.082. Okay, and this our temperature T has to be in Kelvin, and this our P, guys, has to be in atmosphere, then V has to be in dm cube. So if we convert everything, guys, and put everything, guys, knowing fully well that 760 millimeters mercury simply corresponds to 1 atmosphere, so we are just going to put our P to be equal to 1. Then the volume in this case, which is 204 centimeters square, we convert that to dm cube, knowing that 1 centimeter is similar, what, guys? 10 raised to the power negative 1 dm cube. Everything, we have the cube here. So if we do all these conversions, guys, we simplify, we have an answer of 61.8 grams per mole. That's the molar mass of the liquid. Okay, then now, guys, the next part is saying that chemical bonds and intermolecular forces are binding forces which affect the shape and properties of substances. Command 1. Identify the bond types and the shapes of the species in the table below. Okay, so guys, this is boron trifluoride. And friends, knowing full well that the atomic number of boron is what? 5, right? It's 5. Therefore means that its electronic configuration, guys, on the normal secondary school base, knowing that it has what? 3 valence electrons, right? The valence electrons in its outermost shell are what? Are, are 3. And that's what fluorine, guys, are what? 7. So in this case now, it means that each of these fluorine atoms have to do what? Have to covalently bond with this our boron. Okay, so one fluorine atom links with one electron and the other one links with the other, such that there are no lone pairs created. So in such a case now, since both of them are known metals and each of them they are to bring one electron to be shared, means the bond type in this case has to what, guys? A simple covalent bond. And the shape in this case, wherefore in such a case we have no lone pair of electrons, but we have 3 bonded pair of electrons and no lone pair. The shape has to be a trigonal planar shape. Now guys, for ammonia, you notice that ammonia is simply a very famous compound that we know, right? If this guy wants to undergo bonding, guys, it must undergo a dative covalent bond, in which ammonia normally has 2 lone pair of electrons. Whatever species that wants to bond with ammonia obviously has to have an empty space to accommodate those 2 lone pair of electrons. And since ammonia has 2 lone pair of electrons, guys, and that since ammonia has a lone pair of electrons, and the number of bonded pairs are what? Are in total, we have 3 hydrogen, means they are what? They are obviously um since we have 3 hydrogen atom, right? It therefore means that we have a total of 3 bonds in total in this ammonia molecule. And in such a case, guys, the shape has to be a trigonal pyramidal shape. Great. Now guys, the next part says that aluminium trichloride readily dimerizes in a gaseous phase. We should draw the structure of the dimer and label the different types of bonds present. Okay, now guys, let's look at just our aluminium trichloride just as it is, guys. We simply have, please guys, I'll plead to use just the valence. Okay, I'll use just the valences in this case to actually minimize space. I don't want this whole space to be exhausted by just this. So the valency of chlorine, guys, is 7. So we have this. Keep in mind that the red stars signify what, guys? Signifies the electrons on the aluminium atom. So the valency is what? 3. So that's why we have 3 of them, and 3 of these fluorine atoms have bonded to this aluminium. So that's why. And the green stars, guys, signify what? The electrons found on the chlorine atom. So this is what we have. Each of them will covalently link such that all these are chlorine atoms now are stable, but aluminium in this case is still not stable. That's why it had to dimerize. Then now what happens now is that we have a similar compound like this same aluminium Cl3, the same species, which actually comes now and attach itself. So at the end of the result now, we see that this empty space has to be filled, right? And what can fill this empty space has to be what? Something that is already stable. So we are going to have something similar like this, wherefore this is our aluminium again, which brings its empty space now and joins it with what? With 2 adjacent electrons that were here. Then we have this chlorine atom that is stable. It brings now its 2 electrons now and it shares it now with this adjacent aluminium atom. So at the end of the day now, this is what we have. Okay, this is what we have. Now the question wants us to label the different types of bonds. Now guys, do you see that we have these 2 electrons here, wherefore they were brought in by what? By just these adjacent chlorine atoms, and it's been shared by who? By this aluminium, right? And friends, we also have these other 2 electrons this way, wherefore they were brought in by what? By just this adjacent chlorine atom, and it was shared between what? The chlorine atom and aluminium atom. These 2 bonds, guys, are simply uh our dative bonds. Okay, they are our dative covalent bonds, because just one of the species were able to bring it. Then now guys, we also have now at this point now you can simply go to any of these points where you have a red and a green star, and you simply label any of them as the simple covalent bond, because in this case now it is brought forth by all of them. Chlorine brings one, aluminum brings one, and they both share. So this is the simple covalent bond. So guys, these are the number of these are the bond types that exist in this molecule. And friends, this is a structure of aluminum dimer, Al2Cl6. Great. So guys, that's it. There's something you don't understand, friends, please leave it in the comment section down below, guys. I'll get back to you as soon as possible. Let's go to the next question, guys. Let's go. Okay, friends, the next part reads that water and hydrogen sulfide are the two first hydrides of of uh, group 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 5. Yeah, group 6, friends. Sorry, okay, group 6. This is Roman numeral 6, not 5, please. Okay. It said explain why the first is a liquid and the latter is a gas at room temperature. Okay, so guys, water and hydrogen sulfide. So guys, water has to be a liquid because what, guys? Because of the presence of what? Strong intermolecular hydrogen bonds. Wherefore hydrogen sulfide has to be a liquid, because what, guys? It has very weak van der Waals it has very weak van der Waals forces. So guys, water is a liquid because what? It has very strong intermolecular hydrogen bonds. Wherefore hydrogen sulfide has to be a liquid because it has what, guys? Very weak van der Waals force of attraction. Note that these intermolecular forces have the ability to influence the physical nature of species. Okay, it has a huge contribution to play as far as the physical behavior of those elements are concerned, of those elements and atomic species are concerned. So in terms of talking about which one is a liquid, which one is a gas, and why is it so, you simply examine the nature of intermolecular hydrogen bonds that are occurring within them. Note that hydrogen bonding occurs whenever hydrogen is bonded to very high electronegative elements, such as we have oxygen, we have nitrogen, we have fluorine. These are the famous ones. Okay, so guys, know the famous ones. Wait, so this is because of the reason. Then for the next part is saying that the saturated vapor pressure at 100 degrees Celsius of heptane and octane are 791 millimeters mercury and 352 millimeters mercury respectively. Should calculate Roman 1 the mole fraction of each component in the mixture of 25 grams of heptane and 35 grams of octane. Okay, so friends, in this case the best way for us to start is to get the moles of each of them. Let's start with the moles of heptane, guys. Mole is given as what, guys? Given mass per molar mass, right? The given mass here is 25. The molar mass here has to be given as the sum of the individual masses of these our species. So that of carbon is 12. 7 times 12 gives us 84. Then friends, we have that of hydrogen, which is 16. So simplifying that, guys, gives us an answer of 0.25 moles. Then friends, to get the moles of octane, we simply take the given mass, which is 35 as per the equation, over the molar mass. The mass of carbon, like I said, guys, is 12. 8 times 12 is 6, is 96 plus 18. Simplifying that, guys, gives us an answer to 3 decimal place of 0.307 moles. Okay, now that we have this set up, guys, we simply need to go ahead now to get a mole fraction of each component. So the mole fraction of heptane, guys, is given as the number of moles of heptane now divided by the sum of the moles of the two species. So we have 0.25 divided by 0.25 plus 0.307, answer of 0.449. The mole fraction as well, guys, of octane as the demand of the equation give us is simply going to be the moles of octane divided by the sum of the moles of the two species. So we're going to have 0.5551. If you want to check if your answer is correct, guys, sum up these two values, you should get an answer of 1. Great. So guys, this is the mole fraction of each component. The Roman tools want us to get a partial pressure of each component in the mixture. So guys, the partial pressure of the first one, heptane, is simply given as the mole fraction of heptane times what? Its saturated vapor pressure, which is simply what, guys? 791. So if we do that, we have an answer of 355.16 millimeters mercury. Then to get the partial vapor pressure of octane, we do it similarly by taking a mole fraction of octane, multiplying it by what? Its saturated vapor pressure. This one gives us an answer of 193.95 millimeters mercury. Great. So guys, that's how we can solve this particular question. The next one is saying that what do you understand by pH-based solution? So guys, by definition, the pH-based solution is simply given as the negative log of the hydrogen concentration. So this is how it is defined. It's defined by the equation pH equals to negative log of the hydrogen concentration. Great. Then now the Roman 2 wants us to get a pH of 0.01 moles of sulfuric acid. Okay, friends, for us to get this thing done, you might be tempted to just put 0.1 mole into this one, right, and just compute the result. Well, that won't be correct. Why? Because for every 1 mole of sulfuric acid, when it dissociates, guys, it releases what? 2 moles of H plus and what? 1 mole of sulfate ion. But our main interest is what? The 2 moles of H plus ion. So to get a pH of this, we have to multiply the concentration of this sulfuric acid by 2. Since it releases 2 moles of H plus, we're going to have pH equal to negative log of 2 times 0.1. That, guys, give us an answer of 0.7. Wait, so that's the pH of this acid. Then now, guys, the B part is in that a solution prepared by mixing 75 cm³ of 0.1 molar HCl and 25 cm³ of 0.1 molar sodium hydroxide solution. Okay, they want us to get a pH. Now, guys, this is a case where we really have to reason. Let's reason, guys. Let's reason. Now, since we have the molarity of the two solutions, let's start by getting the moles. Okay. So, guys, we start by getting the moles of HCl acid. You can see that what is given as what? Molarity times volume. Because number of moles, guys, is given as molarity times volume, not so. So the molarity of HCl acid is 0.1, and the volume is what? 75. But we need the volume to be in dm³. So we convert that, we have 0.075. Simplifying that, guys, give us an answer of 0.007 moles. Then to get a moles of sodium hydroxide, in a similar manner, we take 0.1 times 0.025, converting it from cm³ to dm³. That gives us an answer of 0.025 moles. Okay. Now, guys, now that we have the moles of the two components, we can see that the number of moles of HCl is more than that of sodium hydroxide, right? So it means that the resultant solution after mixing the two of them now is acidic. Okay, the resultant solution is acidic, and the number of moles of that solution is 0.075 minus 0.025, which we see an answer of 0.05 moles. Great. Now, guys, let's simply note that the volume, the total volume in this case, guys, is given us for the sum of the two individual volumes, right? Because this, our resultant solution, is contained still within that solution, and the volume of that solution is 75 cm³ plus 25 cm³. So now, guys, in this case, now to get the molarity of the resultant solution, we simply take what, guys? Molarity equals to what? Moles over volume. The moles is what, guys? Is 0.005 moles. The volume is what? 25 plus 75, which is what, guys? 100. But converting it to dm³, guys, we have an answer of 0.01. So find that we have 0.05 molar as a concentration. Then, guys, we can therefore use our formula for pH, which is given as what, guys? Negative log of the hydrogen concentration. So we're going to have 0.05. Simplifying that, guys, you have an answer of 1.3. So, guys, that's the pH of that solution. Great. So, guys, if there's something you don't understand, let me know in the comment section down below. I'll get back to you to make you understand the concept as soon as possible. Let's go to the next question, friends. Let's go. Okay, as you can see, the next question is saying that the following data was obtained from the reaction A plus B equal to C. These are the various data that we have. Then the Roman one wants us to determine the order of reaction with respect to the concentration of A and as well that with respect to B. Okay, now guys, let's, if we want to be able to get the order of reaction with respect to each of them, guys, we have to keep one constant and observe the effect upon doubling or upon altering the other. Okay, so what we have to do now is that let's start with A, guys. Let's start with A. Do we see that in experiment 1 and 2 they've kept the concentration of B constant? Because here we have 0.1 mole per gm cube. Here we also have a 0.01. What has happened to B, friends? They have doubled it, right? From 0.1 to 0.2, they've doubled it. So what has happened to the rate of the reaction, guys? It has simply gone from 5.2 times 10 raised to power negative 6 to what, guys? To 2.2 times 10 raised to power negative 5. Note, guys, note. This is very, very important. Please note that also, in as much as you have to pay attention to the whole number part, right? Pay attention most importantly, guys, to the 10 raised to power something. What is up here? Because what is up here is negative 6, here is negative 5. This holds, the first value is smaller than the second, so there's an increase. How? By what amount, guys? By what amount? By an amount of 4. Because if you take 4 times this amount, you simply have this. So friends, it never means that if you want to examine from experiment 1 and 2, guys, keeping the concentration of B constant while doubling that of A, guys, we can see that the rate of the reaction with respect to the concentration of A, guys, has simply done what? Has simply increases by a factor of 4, or it has done what, guys? It has simply quadruples. That's the word, guys. It has simply quadruples. Quadruples simply means that what, guys? It has increased by a factor of 4. So that is why the order of reaction with respect to the concentration of A, guys, is second order. Now, to get that of B, friends, we simply have to look at these our experiments, look at where the concentration has been kept constant. Do you see that, friends? If we consider experiment 3 and experiment 4, we have 0.1, 0.1, guys. They have doubled this one from 0.3 towards 0.6. What has happened to it, guys? That's been increased by what? A factor of 2. So in this case, guys, if we keep experiment from experiment 3 and 4, if we keep that of A constant and double that of B, we can see that the order of reaction with respect to B is what, guys? First order. Why first order? Because what? This our value has increased by a factor of 2. If you multiply 1.665 times 10 raised to the power minus 5 by 2, you're going to have this same expression beneath this order. Okay, this is what you're going to have. So whenever the rate increases by a factor of 2, it is second order. If it increases by a factor of 4, guys, it is second order. By a factor of 2, it is first order. If the rate does not even change, it is what? Zero order. So the order of reaction with respect to the concentration of B, guys, is first order. Now, Roman 3 wants us to write the overall order of the reaction. So, guys, the rate of the overall order of this reaction, guys, is simply defined as the sum of the individual orders of the reaction. So we are going to have 1 plus 2, which gives us 3. Okay. The next part also is to write the rate expression for the reaction, which is to be given as rate equal to what? K, concentration of A raised to its order. Its order is 2, so we have this raised to the power 2. That of B is 1, so we just have B just like this. This is just what we have, guys. That's it. Okay, that's it. The next part is saying that we should write that an atom is composed of 3 fundamental particles. Complete the table below with respect to these particles. Okay, guys, let's observe the trend. Name of particles, we have neutrons. The relative mass is 1.0. It was, oh my god, friends, the table below has been completed already. Okay, I've completed it already. Please, I've completed it. The ones in which you see in right there were the unknowns, but somehow I've simply inserted the answers. Okay, I've inserted the answers, please. The name of the particle in this case, guys, that's a relative mass of 1. And the person who discovered it was Chadwick, is obviously the neutrons, and the experiment he used, guys, was the beryllium foil. Okay, the bombardment of the beryllium foil. That's it. Then the next, you have the protons. The relative mass has to do with the discharge. Oh my god, guys, this wasn't supposed to be it. Okay, the scientist who discovered it was what, guys, was J.J. Thomson, right? It was J.J. Thomson. The experiment used was what, guys? The discharge tube. Wait, the discharge tube. Okay, that's it, friends. The last part of this our section is saying that the following information was obtained from a spectrometer trace of zinc sample. Use the information to determine the relative atomic mass of zinc. So friends, when you see questions like this, it becomes very easy for you because you need to score the marks, right? So for us to get the relative atomic mass of zinc, guys, that's not an issue. Knowing that the RAM of zinc, guys, is begotten by taking each peak value, multiplying it by its mass, plus 0, plus each one multiplies by its mass, because we have peak number of 4, the mass is 64, right? So we have 4 times 64 plus 3 times 66 plus 1 times 67 plus 2 times 68, all over the sum of the peak numbers, that is 4 plus 3 plus 1 plus 2. Most mathematical students are going to do is to divide it by the sum of these ones we have here. No, guys, we divide by the proportion in which each of the isotopes are occurring. Okay, that's it. So we have over 10. If we simplify, guys, we have an answer of 65.7. So guys, do you see that this answer even makes much sense? Because between these our two values, which one is close, which one has the largest percentage occurrence here? We have 4 and 3, right? These are the two biggest. And you see that this 65.7 is between this 4 and 3. It's somewhere in between, right? Yeah, that's a good sign to tell you how correct your answer is. Okay, guys, that's it. Let's go to the next part, guys. Let's go. Okay, the part that we have here, it reads that below is a part of the uranium decay series. This is what we have. They're asking at which particle is emitted in A and B. So friends, this is not even a question, because knowing full well that in an alpha decay, guys, if an alpha particle is being emitted, it ever means that the mass number has to decrease by 4, and the atomic number has to decrease by what, 2. So in this case, we have 238, we have what, 234. Mass number has done what, has decreased by what, 4. Atomic number has decreased by 2. And if you look at B, guys, if a beta particle is being emitted, it means that the atomic number has to do what, has to increase by 1, but the mass number has to be the same, because the beta particle, guys, is massless. Okay, it has no mass. So we can just simply say that the particle emitted at A is an alpha particle, while that at B is what, a beta particle. Wait, that's it, guys, that's it. Then now the next part is saying that if a beta particle is emitted in a process C, identify the isotope X. Like I said, guys, what should happen to the atomic number, that is the number written as a subscript, it has to what, guys, it has to increase by 1, right? From 91 up to 92, but the mass has to remain the same. So we need to have our X whose mass remains the same, but atomic number has to go up by 1. So we have, instead of 91 here, we have 92. Great, that's it. Then the D part is saying that name any 2 ways of close packing of identical atoms such that the environment of each atom is the same with that of the other. Oh my god. So friends, we simply have hexagonal, cubic, hexagonal and cubic closed packing. This is a direct question, guys. It's so direct. Now the next part is saying that in an X-ray diffraction experiment on a sodium chloride crystal, a first order diffracted ray occurred at an angle of 22.77 of 22.77, it's actually in degrees. Given that the wavelength of the X-ray is 0.153 nanometers, calculate the distance between the layer of the ion in the crystal. Okay. So now, guys, we simply have to get this by the Bragg's equation. So, guys, according to the Bragg's equation, which says that 2d sine theta is equal to n lambda, since they're talking about the distance between successive layers, means our n in this case has to be 1. So making d the subject, we have d to be the same like lambda over 2 sine theta. Plugging in all the values, we have d to be the same like 0.153 times 10 raised to the power negative 9 over 2 sine of the angle is 2.77. So simplifying this result, guys, we have d to be 2.96 centimeters. Wait. Alright, that's it. Now the next part wants us to define the following terms. We have standard enthalpy of atomization of an element. Then B, we have bond energy term and lattice energy. Okay. So guys, standard enthalpy of atomization of an element is simply the enthalpy change when 1 mole of a substance in its standard state, guys, is converted into a gaseous atom under standard conditions of 25 degrees Celsius, guys, and 1 atmosphere. Note, guys, note, this condition must be included because this is standard enthalpy this is standard enthalpy, and it only happens when these conditions have been maintained. Okay, it happens only when these conditions have been maintained. So guys, that's it. Now the next question talks about the bond energy term. So guys, the bond energy term now is simply defined as the average bond energy per mole of a particular covalent bond, guys, in a range of covalent compounds. So if you are able to simply take the average of all the bond energy values, guys, divided by the average of all the bond energy values, guys, taking into account the nature of bonding in those compounds, guys, what you get after doing that is simply the bond energy term. Okay, so guys, that's it. The next one talks about lattice energy. Lattice energy, guys, is simply the enthalpy change of formation of 1 mole of an ionic compound from its constituent gaseous ions under standard conditions of 25 degrees Celsius, guys, and 1 atmosphere. Great. So, guys, once you hear about the word standard, means these conditions must be put in place. 25 degrees Celsius, or you can say 298 Kelvin, and 1 atmosphere. They must come into place, guys. That's it. Okay. The Roman 2 says I should write an equation that represents the standard enthalpy of atomization of methane. Oh my god, guys. We simply take methane, guys, and we simply convert all the elements that make up methane into gaseous forms. So we have CH4, which gives us carbon to gas plus 4H. All of them have to be in gaseous states. Great. Okay. So you might ask me why methane here is a gas. The natural form of methane at room temperature, guys, is a gas. Okay, methane is a gas, friends. It's a gas. Okay. The next part is saying that give the standard enthalpy of atomization of given that the standard enthalpy of atomization of methane is 1662 kilojoules per mole. Calculate the energy bond, that's the average bond energy of the carbon to hydrogen bond in methane. Okay, so guys, let's picture how methane looks like. Methane simply has 4 hydrogen atoms attached to it, so which means that the carbon to hydrogen bonds linking the molecule of methane, guys, is what, guys? We have 4 of them, right? We have this one, this one, this one, this one. So it means that 4 times the energy, 4 times the bond energy term, the bond energy of methane, that's the carbon to hydrogen bond energy, has to give us what? Has to give us the enthalpy of atomization, which is equal to what? 1662. If we divide all through by 4, guys, we have the energy we are looking for to be what? 415.5 kilojoules per mole. Great. So guys, that's the solution. That's it. Like I said, guys, if there's something you don't understand, friends, please let me know in the comment section down below so I can understand. I can understand what you're talking about, guys, and explain to you for you to understand so well as soon as possible. Okay. Now, the next part, let's go to the next part, guys. Let's go. The next part which that state the equilibrium law. My god, guys, this is the longest law in chemistry so far. I think at the advanced level chemistry, this is the longest. So guys, but it's very easy if you understand what actually is happening. So guys, the law simply states that the equilibrium law states that for a system that has attained equilibrium, the ratio of the product of the concentrations of the products, each raised to their stoichiometric coefficients of the balance equation, to the product of the concentrations of the reactants, each also raised to their own stoichiometric coefficients of the balance equation, guys, is a constant. Okay, it's a constant. So friends, don't panic. I'm going to explain to you what this law is talking about, but this is how it states. It's somehow lengthy, right? But it's easy to understand once you understand what exactly is happening. Okay, the next part wants us to do what, guys? That the ester ethyl ethanoate may be produced by the reaction. This is the reaction. They are saying that given that initially 1 mole of each of ethanoic acid and ethanol were initially mixed together in a 1 liter container. Now, what they want from us now is that and at equilibrium, 0.8 moles of ethanoic acid was found to be present. Should calculate the value for the equilibrium constant Kc and state its unit. So friends, this is the equation that we have of which esters are being produced. So we know that at equilibrium, guys, at equilibrium, the amount of the mole of ethanoic acid that was there was what, 0.8, right? Since in this case, guys, we are fortunate that the mole ratio in this case is 1:1, right? It means that if what we have here is 0.8 moles, means what we have here has to also be 0.8 moles. And if here is 0.8 moles, it therefore means that what has to be on the right hand side has to be what, guys? 1 minus this, right? Which has to be 0.2. And here has to still be 0.2. Now, guys, what does the equilibrium law states? Its expression, you see that Kc is equal to what, the concentration of the products. We start with water, raised to what, the coefficient of the equation is 1, 1. Everything is 1, right? So we just have this. Okay. So if we, and since in this case now, guys, the two substances are being what, are being held inside a volume of 1 liter, right? So we can simply ignore the volume because the volume is the same for both cases. Normally the molarity is given as what, mole over volume, right? But since the volumes are the same, they can cancel. So we have to deal just with a mole. So we are going to have 0.2 times 0.2 over 0.8 times 0.8. Simplifying that, guys, we have an answer of 0.0625. Great. So guys, that's it. And since in this case, guys, we are dealing with the ratio of two things, right? Two identical things. So it therefore means that our case in this case is unitless. It has no unit. So this was somehow kind of a trap. Now the next part was also to write a cell diagram for the cell formed when the half cells of A and C are coupled and calculate the EMF of the cell formed. Now friends, note this important chemistry. Note it, friends. Note it. It's very important. Always note that the half cell undergoing oxidation is the one that has the smallest E theta value. Okay, the one that has the smallest E theta value is the one that is actually the one that actually undergoes oxidation. So in this case now, friends, the one that undergoes oxidation now has to, what, guys, has to be the smallest, right? Which is simply what, the first. Okay, but in this case, friends, does this one look as if it is undergoing oxidation? It does not, because it's rather doing what, gaining electrons. So it may be good. One way in which you can get this thing done is to rewrite this first equation in reverse order and change the sign of this. Okay, change the sign of this, but in this case, guys, I'll just leave like that. Let's simply go ahead to write a cell diagram of this our equation, knowing that by convention we have to start with what, guys? We have to start with a salt bridge, right? A salt bridge that is two parallel vertical arrows, strikes. Okay, two parallel vertical lines by convention. Then, guys, the one undergoing oxidation must be to the left, and the one that is more oxidized has to work closer to the salt bridge. So if we do that, we have our Fe2 pluses. It is more oxidized than Fe, so we have Fe2 plus in an aqueous medium. Then friends, the meaning of this vertical red barrier is that the physical state of this our ion is different from this, so we use straight lines to separate them. If they were both the same, guys, would have used but just ordinary comma. Okay, then now guys, what has to be at the left now has to be the other, that is knowing that the one that is more oxidized should be beside. So we have H plus, then we have O2, we have water, and we have to end up now with platinum. That is simply the electrode platinum. Okay, that's it. Then we want us to calculate the EMF of this cell. So guys, you know the EMF of this cell is given as the difference between the highest and the lowest. So we are going to have 1.23 minus 0.44, which we have an answer of 1.67. Great. So that's it, guys. That's it. Or if you succeed in writing this in reverse order such that you see oxidation happening, that means that the EMF of this cell is going to be given as the sum of the two of them, because when you must have reversed, this guy must have changed from negative to positive, right? Summing the two of them, guys, you still have the same answer. Now the last part is saying that I should explain why chlorine gas cannot be stored in an iron vessel. Oh my god, guys, you should never store chlorine on the iron vessel. This is because, guys, chlorine gas is very, very reactive. When you place it with that iron, guys, it can simply react with the iron to form iron trichloride, which can lead to corrosion and can damage the compound and can damage your chlorine gas. Okay, you can contaminate it. It's highly corrosive. Great, that's it, guys. That's it for this particular section, guys. If you want to look at inorganic chemistry and organic chemistry, guys, just simply leave a comment in the comment section down below, and don't forget to subscribe to the channel, guys. Importantly, friends, make sure you like this video. Give the video a like, because that's a way of motivating me, telling me that you found the content useful. Have a blessed day, friends.